Hello and welcome to lecture 7. We continue our discussion about degenerate perturbation theory, but we first will discuss whatever we have learned in the previous lecture. And if you remember that our starting point always was this total Hamiltonian, which had a part which we called the unperturbed Hamiltonian, and also another part which we call the perturbation. And you remember that this H naught, that is the unperturbed Hamiltonian, is known, and we have the eigenvalues corresponding to H naught as E1 0, E2 0, and till En 0, and after which there are capital N number of values for which all the eigenvalues of H naught are same, and then again it can actually go to E small n plus capital N, and similarly it can go ahead with this series. So the important point here is that one can actually find out the set of n energy eigenvalues which are degenerate and all have the same value En naught. And if you remember, we have said that the corresponding eigenstates corresponding to these degenerate eigenvalues are denoted like this. It's denoted by ket n naught semicolon 1, ket n naught semicolon 2 up to ket n naught semicolon capital N. And these eigenvectors forms an orthonormal basis in a space which we called degenerate subspace, and which we had denoted with this expression V sub n. Now, we also recall that if we use our unperturbed Hamiltonian onto any one of these unperturbed eigenstates n naught semicolon k, then it is going to give us the same value of the energy. The eigenvalues for these things will always be En naught, with, remember, with this k always running from 1 to capital N. This is to say that suppose we are talking about the hydrogen atom and its first excited state, then hydrogen atom first excited state means we have n equal to 2 first excited state, small n, the principal quantum number equal to 2, and the degeneracy, if you remember, in the hydrogen atom goes as n square if you neglect the spin. Then there will be 2 square, that means 4 states with the same value of the energy. So in that case, this value of k should run from 1 to 4. So that's what this notation n naught comma k means. And also we remember the orthonormality criteria between these orthonormal basis vectors, which we have denoted by n naught p, n naught l equal to delta p l. But then you ask, is this all? Of course, this is not all. Then there are this kind of states where the energy is different. So the non-degenerate states are also there. So your total space for the problem is not only Vn, it also has another part which we have denoted here by V tilde, and then the total space, this curly H, is a direct sum of Vn and V tilde. So this V tilde is basically spanned by the eigenstates of H naught which are not in this degenerate subspace. So the degenerate subspace only contains the states which are degenerate. But one of the criteria that you should always remember that holds between this Vn and V tilde is that Vn is always perpendicular or orthogonal to this V tilde. This means that the inner product of any state outside the degenerate space with a state in the degenerate space is always 0, and that we have written here. And also we also note that the two eigenbases or eigenvectors in the V tilde obeys this orthonormality criteria P naught Q naught equal to delta PQ. Now you also recall that when we discussed the non-degenerate perturbation theory, we had this kind of relation that this unperturbed eigenvector was orthogonal to the perturbed or higher order corrections. Here also the same thing holds. We have a relation like n naught k bra npk ket equal to 0 for any value of p which is greater than or equal to 1. For example, this will actually lead to something like n naught k with n1k or n naught k with n2k. All these kind of things in our products will be 0. But here is a catch that npk still can have a component along n naught l, with l being not equal to k. Therefore, this object, the higher order correction to the state npk, can still have components in the degenerate subspace. So then the next step that we had followed was this n naught k. I know that if I perturb, I can actually expand it in a series of like this nk lambda, because this will depend continuously on the small parameter lambda, as n naught k being the unperturbed state, then lambda n1k plus lambda square n2k and so on. Similarly, En naught, the perturbation, will give us, some correction to the energy, which can be written as En naught. These were the unperturbed energy values. Then lambda En comma k 1 plus lambda square En comma k 2 plus order lambda cube. Now certain statements are in order here. This is regarding the notation which we have discussed in the previous class. We have used two labels to denote this correction to the energy. The reason for using two different labels is the fact that corresponding to different k values, there may be four different states, and corresponding to four different states, once you apply the perturbation, these four different states can vary with lambda differently. Therefore, it is mandatory to write this index k here, because all the states will not be the same varying with lambda. It will actually be different if the degeneracy is completely lifted. Then we use the same trick that we had applied for the perturbation theory in case of non-degeneracy. We had written down this total Hamiltonian H naught plus lambda H1, and we operated this on this perturbed state, and what we get is basically on this total state, and what we get is basically Enk, the corrected values of energy, and we will just replace these Nk lambda and Enk from these equations, from these two equations, and we will have a polynomial in lambda. So this polynomial in lambda will have different powers of lambda, and as you know already many times we have done this, the coefficients of different powers of lambda should separately be 0. So these are the equations up to order lambda square that we have derived in the last class, and this exactly goes in the same manner that you have followed in case of non-degenerate perturbation theory. So there is no complicacy in that. Now we will discuss, as I said, a solution to first order for the case in which the degeneracy in the degenerate subspace Vn is completely lifted off or completely broken in the first order itself in perturbation theory. That is, the first order correction to the energies split these n states which are having the same energy values completely. And for that, in the last class, I had given you a prescription which contained 3 different steps, and we had actually applied the first steps where I said that you heat the order lambda equation, that means this equation, with bra n0L to learn 2 things. Firstly, you can see that H1 must be diagonal in the chosen basis for this degenerate subspace Vn. That is the first important result which I have written here, which we have shown in the previous class. And secondly, you follow the same step and show that what is the value of your first order energy shift, that also we had calculated. So today what we are going to do now is that we are going to follow the next 2 steps to figure out 2 different things. If you remember, the second step was you use the order lambda equation, that means again this equation number 9, to calculate the components of N1k in the V tilde space. Remember, I already said that this Vn, although actually was the degenerate subspace, the rest of the non-degenerate spaces states actually are residing in this V tilde space. So that is the next step where we are going to calculate the components of the first order correction to the state in V tilde. And we have said that there is a reason that this N1k should have a component in this V tilde. And the last step was to hit the lambda square order equation, that means this equation number 10, with again N0L bra to determine the second order correction to energy, which we had denoted by ENK2, this one. And the component of N1k, the first order corrected states in the degenerate subspace Vn. So that was the steps that I had mentioned, and today we are going to follow these 2 steps. So let us first talk about this step 2. That means, as we said, we use the order lambda equation, which is nothing but H0 minus En0 acting on ket N1k. This is equal to En comma K1 minus H1 N0 K. So this was this order lambda equation, this equation number 9, this equation. So what you do is that you operate with bra P0. Remember, this P0 were the elements of V tilde. So you operate this bra P0 from the left side on this equation, and let us see what we get. we will have N1K kth here, and then P naught E1 n comma k minus H1 n naught k. So this is what we are going to do, but you already know that this unperturbed Hamiltonian acting on this state P naught, which is non-degenerate, will give you the value E P naught. And then this will already be there, so we will have E n naught also, and then we will have the inner product P naught n1 k. So that's the left hand side, and then here we will have this thing E n comma k1 minus h1 n naught semicolon k. Now let us look at this object. What is this thing? You note this important thing that n1 semicolon k is unknown to us at this stage. That's what we are looking for. We don't know what it is, and I am getting the component of this unknown correction n1k along the v tilde space. So this means that we can know the component of the unknown quantity n1k along v tilde space. So this is what this inner product will tell us. Now look at the right hand side. What is this object P naught bra? This is an object or a vector in v tilde. This belongs to v tilde. This n naught k, it belongs to the degenerate subspace Vn, and this one enk1 is just a number. You already know that this is just a number. But we also said that v tilde and Vn, these two spaces are orthogonal. Therefore, these already implied P naught n naught semicolon k should be equal to 0. So this means that the first term on the right hand side, P naught enk1 n naught k, this enk1 should come out, and we will have an inner product P naught with n naught k that is going to give us 0. So this term therefore goes away. What we are left with is basically P naught n1 semicolon k is equal to minus P naught h1 n naught semicolon k divided by E P naught minus E n naught. And we can also write it in a short form. That means this object is nothing but the matrix element of the perturbation matrix within the degenerates or between a degenerate state in Vn and the other state which is outside of Vn, that is in v tilde. So this is nothing but minus h1 p comma nk, that's the notation we were using, divided by E P naught minus E n naught. So this is a result which gives us something which is interesting, that this object is still my unknown. I really do not know what are the matrix element of the perturbation matrix H1 between the states, one of which is in the degenerate subspace Vn and another of which is in the V tilde which is outside Vn. So this quantity needs to be evaluated. Now note one thing also, the factor EP0 minus En0 is non-zero. This is important and this is also required, because if this is 0 then we are in trouble. So the factor EP0 minus En0 is non-zero. Why? Why it is non-zero? It is because all the states which are denoted by this P0 that are in V tilde, belonging to V tilde, have different energies than our degenerate ones. Have different energies than our degenerate ones, or degenerate energies, En zeros, because all the degenerate states at the unperturbed level the energies are En zero, and of course these are not same as the non-degenerate energy eigenvalues. So now you can still work on this equation, continue work on this equation, and you can just write this object n1 semicolon k as sum over p naught bra p naught n1 k. So this you can explain by just recalling that if I give you a vector psi and if you write it in the eigenbasis phi I with the coefficient ci with the summation over I, you can immediately figure out what are its coefficients ci. The ci coefficients are basically nothing but phi I ket psi. And you can therefore use this result here to write your psi ket psi as sum over phi I psi. So this is exactly the same thing that has been done in this step. And why did we do that? We did that simply because this object is known. So I can simply replace this object from this equation. So what we get here is nothing but minus sum over p h1 p comma nk divided by e p0 minus e n0 with the ket p0 sitting here. So this is my n1 semicolon k, where remember these p0 ket vectors are the basis vectors in the V tilde space. But now you ask this question, is this equation correct? Is this equation completely correct, technically correct? The way we have written this equation is not actually correct if I talk about technicalities, because you see that the left hand side is not just ket N1K. Rather, it is the component of N1K along V tilde. Why it is that? This is because we took the inner product of P naught with N1K, and this tells us how much of N1K is there along P naught. That's what I have written here somewhere. Where did I write? Yes. This actually tells us, this object, that how much of N1K is along the V tilde space, or more precisely along P naught. That's what this quantity gives us. So, this equation rather should be written as N1K in V tilde is equal to minus sum over P H1 P comma Nk, the matrix element, E P naught minus E N naught P naught. So this is what is extremely important here. Technically, the equation that I had written in this step is not correct, because we have started with N1K projected along the direction P naught, which is in a different space which we have called V tilde. Therefore, this quantity is not exactly, this N1K ket is not fully N1K, the full N1K is not here. It only gives us the N1K in the direction of P naught. Therefore, this is nothing but N1K in the V tilde direction. So let us call this equation 11. This is very important to note at this stage. Therefore, we can safely write that N1K, the full N1K, as we already know, has a component along V tilde and along Vn. So I should write it as N1K V tilde plus N1K Vn. But we already have evaluated N1K along V tilde, so I will substitute that, and this will be H1 P Nk E P naught minus E N naught P naught ket plus N1K along Vn. So this is my full N1K. This is my full N1K. So let me put it in a box. This is very important equation, and let me call it equation number 12. So the next thing that we need to do is that we need to find this N1K along Vn to find the complete correction to the state N1K. So this is the state correction to first order. N1K ket is the state correction to first order. So we just have seen that this N1K state can have components along both these Vn and V tilde. We have just now found out the component of N1K along V tilde direction. What remains to be calculated is the component of N1K along the Vn direction. Now at this stage, let us stop and think a little bit. We actually take help from our non-degenerate perturbation theory. There we had used the order lambda equation to calculate fully the correction to the state N1. Remember, there was only one label to denote the non-degenerate state, which we said N1, ket N1. However, in the degenerate perturbation theory, it is clear that order lambda equation has been used fully, but we still did not find a part in this N1K. This N1K, we only had figured out the component which is along V tilde. We were not able to figure out what is the component of N1K along Vn direction, or in the degenerate subspace direction. That we have still not found out with the help of the first order equation only. In fact, we ran out of information from order lambda or first order equation now, and therefore we need to use the next equation, which is order lambda squared equation, to actually rescue us from this complicated scenario. So now you have to go to order lambda square equations to find the first order correction to the degenerate part of the state. This is in stark contrast to what you have done in non-degenerate perturbation theory. And that is the reason this degenerate perturbation theory is kind of infamous for all these complications. So, let us actually take the third step. And what was the third step? The third step was, we said that you hit the order lambda squared equation with this bra n naught L, which is in Vn, to determine two things. One is the second order correction to energy, which we had denoted by ENK2, and the component of N1K along the degenerate subspace. So we will calculate both these things from the order lambda squared equation. So the thing is that we hit the order lambda square equation with N0L, and we see what is in store for us there. So what was the order lambda square equation? The lambda square order equation was this one, H naught minus En naught. If you remember, this is very easy to remember. This unperturbed thing always is acted on the highest order, and then the first order correction comes like ENK1 minus the perturbation metric and the first order corrected state. Both of are order lambda, so that is why this is a lambda square equation. And then of course the second order correction to energy ENK2, and this must be the 0th order correction or the unperturbed state. So that's very easy. You don't need to actually calculate anything explicitly. If you remember how to calculate this thing, then just by arguing in this manner, this one is the second order correction, this one is second order correction in energy as well as in state, therefore this is order lambda square. Similarly, this one is the second order correction in energy, therefore it must be 0th order or the unperturbed Kate. So that is how you write down your equation here. And then, as I said, you hit this equation by bra N0L from the left. So do that. If you do this, we will have H naught minus En naught N2 semicolon K, and then this is N naught semicolon L ENK1 minus H1 N1K plus N naught L ENK2 N naught K. Now you can see that when this H naught acts on N naught L, it will give us one En naught, and this En naught and this En naught will get cancelled. So on the left hand side we will always get 0. So the left hand side will be 0, and what remains on the right hand side is the following: n naught semicolon L E n k 1 minus h1 n1 k plus n naught L n naught k, because E n k 2 is just a number. So this I know already that this is nothing but delta Lk. So the equation therefore remains like this, that n naught semicolon L E n k 1 minus h1 n1 semicolon k plus E n k 2 delta Lk equal to 0. This is our equation now. Now comes the problem. The first term here in the left hand side of this equation, this first term, this term has n1k, which has parts in the degenerate subspace Vn as well as in V tilde. So we have to write this by breaking this object into two different parts, two different components. So we will have something like this: n0 semicolon L E n k 1 minus h1 n1 semicolon k, let us write this as V tilde, and the second term will be n naught L E n k 1 minus h1 n1 semicolon k, this is along Vn, plus E n k 2 delta Lk equal to 0. So from this step to this step we have done nothing new. We have just said that this object ket n1 comma k has components along both the directions. One is along V tilde, another one is along Vn. So we just broke this n1k vector into its component. Now again, in this first term here, this first term, if you look carefully, this en k comma k 1, this object is just a number, and n0l and n1k, n0l is in the degenerate subspace and n1k, this one is along V tilde, is in V tilde, and therefore n0l n1k inner product will be 0. So let me write this. Since n0l is in Vn and n1k V tilde is in the orthogonal space, therefore their inner product will be 0. Therefore we will not get any contribution from the term which has enk1. So that's enk1 will not contribute to the result at all. So now we have h1 in this second term, and we also have the basis states n0l of the degenerate subspace, and we already know that h1 is diagonal in the degenerate subspace. But now comes the important question. The question is whether n0l operated by the perturbing matrix h1 will yield an eigenvalue of h1. See, we have this H1 sitting here and H1 sitting here. And in both these equations, H1 can act on this object, H1 can act on this object. The question is, we already know that H1 is diagonal in the degenerate subspace, but whether this N0L, when operated by H1, will yield an eigenvalue of H1 or not. The answer is no, and let us see why. This is also very interesting, that the perturbation H1 is diagonalized in the subspace Vn. That we have already seen. The perturbation H1 is diagonalized in the subspace which we had denoted by Vn, the degenerate subspace. The perturbing Hamiltonian H1 is not diagonal in the whole space. That we have to keep in mind. The perturbing Hamiltonian H1 is not diagonal in the whole space of the problem. That means H equal to Vn direct sum V tilde. Only within the block representing Vn is H1 a diagonal matrix. Otherwise it is not. So action of H1 on this bra N naught L may actually take you outside Vn too. That is the first interesting point and little bit complex point that you have to understand. This H1, you might think simply that when we are having N naught L bra and we are actually in the degenerate subspace, can actually give us the eigenvalue, but it is not. The perturbation H1 is diagonalized only in the subspace Vn. The perturbation H1 is not diagonal in the whole space. How can I see this? So let me just stop at this equation and let me do a separate calculation and let us come back to this equation. Okay, so let me just number this equation. This equation, let me call equation number 13. And let me do this calculation here. So we have H1, the perturbing Hamiltonian, and suppose it is acting on N naught L. This I can actually write by inserting the identity operators and using the completeness relation like this. I introduce a set N naught Q, N naught Q plus sum over P, P naught, and then acting on N naught L. Let us see what we have done here. This object with this summation Q is identity. So I can always insert this. But this object belongs to Vn, the degenerate subspace. Similarly, this object belongs to V tilde. But this also is identity. So this, therefore, by inserting this identity, we can write N naught Q, N naught Q H1 N naught L plus sum over P naught H1 will act on this N naught L. This therefore can be written as sum over Q E N comma L1 delta L Q N naught Q plus P naught sum over P ket P naught bra P naught H1 N naught L. In fact, why I was able to write this step? Because you remember this object was fully in degenerate subspace V naught, and therefore this object N naught Q H1 N naught L is the matrix element in the degenerate subspace Vn. And we know that in that degenerate subspace Vn, this H1 is diagonal. We have proved that in the last class. And I know that this H1 acting on N naught L will give me E1 NL delta LQ. This we have proved. So this is nothing but this object. So now this is equal to E N L1 N naught L. In coming from this step to this, we have just used this Kronecker delta, and therefore the summation goes away. Plus, of course, this will remain P naught H1 N naught L. This whole object is actually along V tilde. This whole object is actually along V tilde. Let me call it equation number 14. This shows that the states N naught L are almost the eigenstates of H1 with eigenvalues equal to the first order energy corrections, and the failure is just by an extra state along V tilde. So this is very nice. So what does this equation tell us? We have this perturbing metric acting on N naught L, and the result we have received or we have obtained is equation 14. So this immediately shows that states N naught L are almost H1 eigenstates, almost, with of course the eigenvalues E NL1, that is the first order corrected energies. The failure by which it is not exactly the eigenstate with eigenvalue ENL1 is this term. The failure is an extra term, or sorry, I should write extra state because this is a state, extra state, along V tilde, the other space that we had other than Vn, or the degenerate subspace. So with this thing in mind, let us look at our equation number 13 again. So this was our equation number 13, and let us then write this. Okay, I think it's better that we should take this equation as it is from this. And put it here. So this is our equation number 13. So let me write it again. Look at equation 13 with the above information which I have just mentioned here. So what does it tell us? So we have N naught L H1 N1 K is equal to E n comma L 1, because I have H1 n naught L as E n L 1 n naught L plus this object. So this is E n L 1 n naught L n1 K. So I am looking into equation number 13 with the help of this equation number 14. So let me again look at this carefully. We have N naught L H1 and then N1 K. So I will just look at this Vn term. Okay, I am not looking at the full equation. I am just taking this term out and I am looking here. Okay, so this is N naught L H1 N1 K, and we have just shown that H1 on N naught L is nothing but ENL1 N naught L, and then there was this N1K. But then I also have the second term, which is N naught L sum over P naught N1K. And this thing is of course in Vn. Everything is in Vn because we are looking into this term. But this object is already 0 because these are basically from two orthogonal spaces, V tilde and Vn. So we can safely write that N naught L H1 N1K, this along the Vn, the degenerate subspace, should be ENL1 N naught L N1K Vn. Of course, everything here is in Vn, that we have to keep in mind. I just didn't write. So this is the second term. This is good. In fact, you look what has happened because of this, the H1 term in this second term here. The H1 term has become exactly same as N0L N1K. These overlap exactly like the En1K term. So finally, what we have from our old equation, this equation, finally if I take into account everything, so we will have minus N0 L H1 N1 K, but this one is in V tilde, this one is in V tilde. So this is equation 13. This one was the first term. Then we will have this object which I have just written here as ENL1 N0 L N1K. But we also have this term. So we will have something like ENK1 minus this will give us ENL1 and then N0 L N1K, and everything is in the degenerate subspace. And of course there is this term which we need to remember. This is equal to plus En comma K 2 delta L K is equal to 0. Oops. So this, what does this equation tell us? Remember, this object was our unknown. This object we wanted to figure out, N0 L N1K. But as a byproduct, we got the second order correction to energy. This one. Why we are calling that we as a byproduct we are getting second order correction to energy? Simply because you can now set L is equal to K. Let us set L equal to K. And if we set L equal to K, what we will have is minus N0 K H1 N1 K along V tilde plus En comma K1 minus En comma K1. This is going to be 0. K N1K. This was in Vn, and then we had ENK2 equal to 0. Therefore, we can immediately write ENK2 as, so this goes, we have N0K H1 N1K but in V tilde. Several important relations we are deriving today. So let me call this equation equation 15, and let me call this equation 16. But we know this N1K tilde, N1K along V tilde, N1K. What is N1K along V tilde? We have obtained this already. If we go back, yes. So this was N1K, equation number 11 was giving us N1K along V tilde. So this, I forgot. n1k along v tilde was minus sum over p, the matrix element of the perturbing matrix with components along p and nk, that is v tilde and vn directions, divided by the ep0 minus en0. So this is going to be minus sum over p h1 p comma nk divided by ep0 minus ek0 p0. This is what we already know. Therefore, this equation number 16, finally will be Enk, the second order correction to energy for these degenerate states will be n0 k h1 operator, then sum over minus h1 p nk divided by ep0 minus ek0 and then p0. And what it is, this is, therefore I can take this sum here, p, sum over p, we will have n0 k h1 p0, and then we will also have h1 p nk divided by ep0 minus ek0. And therefore it is, this object is nothing but the matrix element of the perturbing matrix, and this is this is nothing but h1 nkp. So this is therefore minus sum over p mod of h1 nk comma p whole square divided by ep0 minus ek0. This is the second order energy correction for the degenerate states. Now look at this formula carefully for a minute. It has the same form as the second order correction to non-degenerate energies. That's exactly the same form, except that you only sum over the states that are outside the degenerate subspace. These are the states which are outside the degenerate subspace. That is the only difference. But otherwise the nature and the formula is exactly the same. But you find, I mean, you already have seen how much effort has gone into to figure out this. So the next question, the final question is, what if we set L not equal to k? Of course, we can always set L not equal to k. Then immediately you see that this term here, where it is, yes, this term here, enk2 delta lk, if L is not equal to k, this term is 0. Now, if we had not suspected that the state n1k had a component along the degenerate subspace, we would not have introduced the second term here at all. This second term here at all would not be introduced if we had not suspected that there is a piece along the degenerate subspace of this vector n1k. And we would have simply, in that case, we would have gotten this object to be equal to 0, because for L not equal to k, this is non-zero, this is 0, and if we had not guessed that this is there, then this would have been 0, which is not correct. It is just not 0. This object is this n1k, whatever you do, it's not 0. So unless we have a second term here in equation 15, this term is very important, which came because we had suspected that there is a component along the v tilde direction, apart from the component being in the vn direction also. So this proves that the state must have a component along the degenerate subspace. That is why you had to have this second term here. So therefore, again you take this 15th equation and then you put L not equal to K, and let us see what happens there. If we put L not equal to K, we will have N naught L and N1 K. These are along Vn. This is the second term, this term here. So this is along Vn, and then it is being multiplied by Enk1 minus Enl1, which is equal to N naught L H1 N1 semicolon K V tilde. That means N naught L N1 K along Vn should be equal to N naught L H1 N1 K divided by Enk1 minus Enl1. This is along V tilde. That's it. So if the degeneracy had not been broken, because we are looking at L not equal to K, if the degeneracy had not been broken, then we would have got 0 in the denominator, because now we are looking at L not equal to K. If L equal to K, then we would have been in trouble. So your degeneracy had to be broken completely at first order. That is correct. So this would not have given sensible result. This equation would not have given sensible result had the degeneracy been not broken at first order, because then we could not have set this K not equal to L at all. Now, so it was a requirement that all the degeneracy has been broken at the first order. Otherwise, one will not be able to compute the state in this manner. Okay. So we are, remember what is our target? Our target is to calculate what is the state correction for these degeneracies, for these degenerate states. So in order to figure that out, we have just seen that in the denominator we have this factor, which would have been 0 if we had chosen L not equal to K, if we had chosen L equal to K. But we have this degeneracy completely broken, so L not equal to K is justified, and therefore this term in the denominator is non-zero. So from here it is very easy to figure out what will be N1 K along Vn. So this will be of course N naught, okay, sum over L not equal to K. Let me put this first. N naught L is there, 1 by Enk1 minus Enl1, then N naught L H1 N1 K V tilde. So that's the full result. We just had done this thing from here. We just had to figure out what is this state N1K. So we just introduced this complete sum here, and we had written this. So we can finally write that this is equal to L not equal to K N naught L 1 by E n K1 minus E n L1 N naught L H1, but we already know what is En1K along V tilde, that we already have that result. So that is minus sum over, okay, this is minus sum over H1 P comma Nk divided by EP0 minus EK0, then P naught, this one. So finally we will get N1K in Vn as minus L not equal to K N naught L 1 by E Nk1 minus E NL1, and then there was a sum over P, of course this was sum over P, then this object N naught L H1, now this H1 acts on this P naught, therefore it's a matrix element H1 NL P, and then we have H1 P comma Nk divided by EP naught minus EK naught. Sorry, I think I have gone wrong somewhere, because this was, yes, this is wrong, this was P comma Nk, we have always used I think N instead of K. So this is the expression for the correction to the state to first order because of the degeneracy. So now I have an observation at this moment, and this observation is very crucial. Is there a problem in order counting here? Because I can see some problem here. Look at this equation carefully. Look at this equation carefully and see if you can find out any problem with this equation. The left hand side of this equation, which contains N1K, definitely is first order in perturbation theory. But now you remember we had to go to the order lambda square equation. And is that why we seem to be counting orders wrong? Because we have this object sitting here, H1 NLP H1 PNK, the matrix element in the numerator, which is second order in perturbation. This object is second order in perturbation. So how come we get a first order term on the left hand side? This is a first order term N1K in the left hand side, that seem to retain a second order term in the right hand side? The answer is that the energy denominator, this saves you. This energy denominator is also first order. So the numerator is second order, but the denominator is first order in perturbation, and hence the ratio is first order. Everything is absolutely okay. Because this ENK1 minus ENL1, remember that each term here has a power of H1. So it is first order in the perturbation. So this ratio, 1 in the second order in the numerator and first order in denominator, will make sure that the whole result is up to first order in the perturbation. So this completes our full discussion of degenerate perturbation theory, where the first order perturbation splits all the levels. So the only criteria that we had used in this calculation, which is of course I agree a little bit cumbersome, but once you understand this thing, it's really beautiful. And it's most of the cases, as I said, in physics you will get degeneracies in three-dimensional problems. You have to handle such degeneracies with these theories. The only assumption that we have used repeatedly in this calculation is that all the degeneracies have been lifted at the first order itself. So first order perturbation splits all the levels. There is no degeneracy. So you still have to do the degenerate perturbation theory where first order perturbation does not split any of these levels. And then you have to go to second order, and that calculation I am not going to probably do in the class. I think that it is going to be a little bit more involved. But of course, I would ask you to solve this, that calculate the degenerate perturbation theory correction to energy levels and the states when the first order perturbation does not split any of the levels. Maybe as a homework or assignment we can discuss this.